Okay. Good afternoon. Thank you for coming to today's seminar, and it is my great pleasure to introduce to you or present to you our own Aljona Blöcker. Aljona did her PhD at the same university that I did, University of Cologne, and even the same department, so 2017, with Joachim Bauer on the modeling of ice in Europa's plasma interaction with the Jovian magnetosphere. Then she stayed 7 months for further analytic modeling of the hemisphere coupling and asymptotic plasma interaction. Then from 2018 to 2020, she was the Maria Sklodowska-Curie postdoc fellow at the University of Stockholm. Lawrence, exactly. When you did simulation is spacecraft data analysis for IO and Europa plasma environment. So IO and Europa stayed a long time, as you can see. And from 2021 to 2023, she was a postdoc at the Ludwig Maximilian University, or LMU, as some people know it, where she did data analysis of Juno spacecraft data. And since October 2024, she is now a postdoc in the group of Christiana Helling's exoplanet climate and weather, where she is studying exoplanet atmospheres and magnetic coupling. And today she is going to introduce us for the whole image.
Thank you very much. Yeah, I'm very happy to be here and to give an introductory talk what I did so far. And because I spent a lot of time doing studying plasma interaction of the Galilean moons, I will mostly talk about this. I started with this studying during my bachelor, and then I continued doing my master, PhD, and also my postdoc in Sweden. When after I switched a bit and did a bit data analysis, but I will not talk about this. And in the second part of the talk, I will talk about what I'm doing here. So just to give you an idea what I'm doing in this group with Ludmila and Christiana. And you see here, these were my main collaborators and supervisors so far. So this is already. So I would like to start with an introduction to the Jovian system. So Jupiter is the largest planet in our solar system. It is also the one with the fastest rotation and also with a strong magnetic field. It creates a huge magnetosphere. And here in the sketch, you see the inner magnetosphere of Jupiter with the 4 Galilean moons, Io, Europa, Ganymede, and Callisto here. And all 4 moons are embedded in this moving magnetized plasma. So the moons orbit Jupiter with a slow velocity when the plasma, which co-rotates with Jupiter. And so the root cause for the plasma interaction is the continuous flow of magnetospheric plasma past the moon's atmospheres. And this is what I was studying too. So the plasma is always in direct connection with the atmospheres of the moons and also the surfaces. And creates this very complex plasma interaction. And it is decisively influenced by the moon's atmosphere. So in our Jupiter's magnetosphere is that Io is the main source of plasma in Jupiter's magnetosphere. Io loses material mostly in form of neutrals, and after some time, these neutrals gets ionized by electron impact ionization, and these newly created ions are then subject to electrodynamic forces from Jupiter. And this plasma then accumulates around the orbit of Io and form the so-called Io plasma that you can see here. So in order to maintain this torus, we need a mass loss rate from Io of about 1 ton per second. So let's have a look on the 4 Galilean moons. So here you see a family portrait of the 4 moons, and you already see from the landscape that they're quite different. They all have very interesting features. Like this 3 outer moons, Europa, Ganymede, and Callisto, are icy moons. They have icy shells, and they might have a subsurface water ocean. Io is different. Io doesn't have any water or water ice, but the sulfur dioxide and sulfur compounds dominate on Io's surface. And the surface of Io is also always changing. Just to give you an idea of the sizes, so Io and Europa are of the comparable size with the moon that we see. And in my during my research, I was looking on Io and Europa, the two innermost moons. I'd like to give you a few ideas or like a few features of the moons here. And here in this movie here from New Horizons spacecraft, you see an eruption of the Twashta volcano with a plume of about 300 kilometers and more. This is a very nice movie. So Io is the most volcanically active body in our solar system with more than 150 hotspots. Io also has a tenuous SO2 atmosphere, and here in this plot you see the day-side atmosphere of Io, SO2 column density with longitude and latitude. And about 50% from this volcanic or from the atmospheric gas comes from volcanic outgassing, and larger fraction is volcanic gas, which goes out and then fall out and freeze at the surface of Io. And when, like at night side, it completely freezes out, and when exposed to sunlight, the SO2 sublimates, which makes about 50 to 80% of the whole atmosphere. And when we observe Io's atmosphere, Io's day-side atmosphere, we see that it's quite stable, but it's also very asymmetric. So here in this column density, you see that at the poles, like here and here, the atmosphere is quite thin. We have about 2% of the density what we have at the equator. We also see that we have an asymmetry between the anti-Geranian hemisphere and the subterranean hemisphere. So it's denser on the anti-Geranian hemisphere. Then we also see an upstream-downstream asymmetry. Upstream side is the side where the plasma collides with the atmosphere. And then we also see a day-night asymmetry. So how did Io become so volcanically active? And the main reason is that Io orbits this massive planet and is in Laplace resonance with Europa and Ganymede. That means if Io orbits Jupiter 4 times, Europa does 2 times, and Ganymede 1 time. So that means that every orbit of Europa, this Galilean moons are, or like these 3 moons are aligned on different sides of the planet. And this fact keeps them on a relatively elliptic orbit. So the gravitational influence from Jupiter always changes along the orbit. And because Io is the closest one, the gravitational influence from Jupiter is also the strongest one. And here in the sketch, you see an orbit of Io sketched. So when Io is closest to Jupiter, it creates this large tidal bulge. And as Io orbits or like travels along its orbit, it relaxes, and we have a small tidal bulge here. So we have tidal heating going on. So we have a relaxing and squeezing of the interior. And this releases energy, which might be enough to melt Io's interior. So and the big question was debated for a long time, and also during my project, does Io have a global magma ocean or not? So, or is it just solid rock with some melt inside? I will come to this later. So the tidal heating is also, so for me, like for my research, it was also like the main question that I was looking on is we have this asymmetric atmosphere, and we have this interior magma ocean. And how do these things influence the plasma environment of Io? So the tidal heating is also the the reason why Europa most likely has a global water ocean. So here you see a sketch of the layers of Europa. So we have a rocky interior, a global water ocean, and above it we have a water ice shell of 3 to 40 kilometers. When you look on the surface or in the landscape of Europa, you see these ridges and cracks which resemble a bit the Earth's polar ice, and also the lack of many impact craters implies that the surface is quite young, so that probably due to subsurface activity that it gets always renewed. Furthermore, we know that Europa has an oxygen atmosphere, or it's more like an exosphere, because it's very famous. So, and here in the sketch, you see how this oxygen is created. So we have charged particles bombarding the water ice or on the surface of Europa. And when these particles, like when they bombard, they take out molecule by molecule and create O2 and hydrogen. So since hydrogen O2 is heavier, the O2 is bound to the surface of Europa. Furthermore, we see also like this kind of dots, white dots. These are pickup ions. So when molecules in the atmosphere get ionized, they will be picked up by the magnetic field and carried away. So another fact about Europa, like in 2014, this moon drew a lot of attention because for the first time, water vapor plumes were discovered in Hubble Space Telescope observations here. And this was a big discovery because this discovery means that we might have a new mean to probe this the water from the subsurface water ocean, and in order to derive astrobiological conclusions about a potentially habitable environment at Europa. But this observation was only done once, and there were a lot of Hubble Space Telescope campaigns after, just looking on this on the south pole of Europa, but we didn't see any water vapor plume. So it's quite a sporadic event. And for me, like I was interested in, if you have this kind of water vapor plume, which was seen here, which is quite dense, how does it impact the whole environment of Europa? So these were the two questions that I was looking on. And since I'm looking on the global plasma interaction, the best method for this is using magnetohydrodynamic simulations. And I will show you, just to give you an idea of the MHD model. So I was using Zeus NP, which is an open source code. So you have different open source codes in MHD that you can download. And when you get like a code which is solving the set of differential equations of ideal MHD, which is like continuity, momentum, induction, energy equation. But to study the effects of the moons, it is not enough. So you have to implement other effects that are important for the plasma interaction, like electron impact ionization, loss, and so on. So this is what I did. So I implemented several effects. I'm not going further into detail, but it's mostly like electron impact ionization, dissociative recombination, then collisions between the ions and the neutrals. And in all this like terms, the atmosphere is included because we want to study how does the atmosphere or the plumes influence the plasma environment. Just to give you an idea how the simulation looks like. So I have here a video. So this is the start. We have a moon in the middle, which acts like an obstacle to the plasma. The plasma comes from the left. So you have here, this is what you see here in 2D, is the plasma bulk velocity. So we have here 57 kilometers per second. This is the start velocity the plasma for EU. The background magnetic field is pointing to the negative Z direction. And when I start the simulation, the plasma arrives at the moon. We have perturbations here, and we have also the propagation of different wave modes. So what is happening here? So plasma arrives here. We have electron impact ionization, collisions between ions and neutrals, and so on. So we have perturbations, and when this perturbation propagate along the magnetic field lines north and south of the moon, this is where we see also that the magnetic field, the velocity field is decreased very strongly in these structures here. The structure we call it Alfvén tubes or Alfvén wings, which are like tubes, and these are from the rest frame of the moon. These are standing Alfvén wings. So let's have a closer look to this. So this interaction that we see at EU and Europa, we call it subalfvénic interaction because the Alfvén Mach number is smaller than 1. We have the propagation of the perturbations which are happening here along the magnetic field lines. The magnetic field lines are frozen into the plasma, and they arrive here, and then you have a pile-up of the magnetic field lines here. The Alfvén wave is also a non-compressional wave. So that means that if you fly quite far away from the moon, if you see here with the spacecraft, right, you will see perturbations here for sure because of the Alfvén wings in the plasma bulk velocity, but also in the magnetic field. But you will not see perturbations in the plasma density. This is why, because of the non-compressional nature of the wave. And this is the cookbook for my simulations. So what I did, I did several models of different atmospheres for EU and Europa. I will show you this later. And maybe I did also a model for a subsurface magma ocean or water ocean for Europa. And I put it in my model when I simulate it and get this global plasma interaction, when I can see or I can study what effect is doing what. And when later I can compare it to Galileo observations. We had a few flyby for EU and Europa from the Galileo spacecraft. So let's talk about Europa. So the neutral atmosphere model that I put in my model, in my MHD model, I show it here. So what you see here is the neutral number density for Europa, and I cut to the moon. And here I also implemented the plume in the south pole. So it's a very easy analytical expression. It's like an exponential function. So it's a symmetric neutral O2 atmosphere with a southern polar plume. And these are the column densities, and this is the plume column density. These numbers are all from what we have from HST observations. So they're consistent with the observations. And you see that the plume is so much denser than the atmosphere. So we have a strong contrast between the density of the atmosphere and the plume. It's about a factor of 100. So, and when I do my simulations, again, the global plasma interaction, no plume here. So just the atmosphere. We have the development of Alfvén wings, where the plasma flow velocity is decreased. It's not only in the plasma flow velocity, also the fields like the magnetic field is perturbed in this area of the Alfvén wings. So when I implement plume, and you clearly see that the plume introduces a strong north-south asymmetry in the wings. So, and what we see here is that inside the Alfvén wing, we have a smaller Alfvén wing. And this we call it the Alfvén winglet, because we have much more, because it's very dense here, we have much more perturbations here. And these perturbations when propagate along the magnetic field lines south of the moon. So this is where we see this very strong decrease of the velocity. So that means also that if we have a plume and we fly quite far away from the moon, we would see a signal from the plume, which is quite interesting. So we have now a method to find evidence for plume at Europa. When I was also looking like what kind of Galileo flybys do we have for Europa. We don't have so many, but I was looking especially ones that go through the Alfvén links. They are 3 in total. And one was very interesting. This is the flyby E26. So here you can see the trajectory passing by. And the magnetic field, which was measured, is shown here in the black line. So this is the Bx component, By, Bz. And you see, like, when this is the closest approach here. So when Galileo is very close to the moon, we see strong perturbations and also small-scale perturbations, which we, in the other flybys, we didn't see small-scale perturbations. It was just a smooth structure. But if I model this plasma interaction for this flyby with a symmetric atmosphere, I get this result here, which kind of fits the main perturbations, but it doesn't give us any small-scale perturbations, right? So what I did then is implementing a plume inside to see what would it do if we have a plume. And you see here, this is the magenta line, shows us the perturbations just due to the plume. So what I see here is that implementing a plume in the atmosphere, like an inhomogeneity, it makes different small-scale perturbations that we also see in the E26 flyby. But we have quite a big parameter space for this because we have an idea of the density of the plume, maybe, but there is also like, is the plume inclined, or what is the scale height of the plume, and so on. There are so many things that we don't know. So we have, like, if I would investigate it, it would take a lot of time. Also, the position of the plume is not clear because it was only seen once, and so we don't really know where it really is. So I also did our plume models, like I shifted the position a bit, and then I get this signal here, which is single here. This shows that the plume signatures in the magnetic field data are very dependent on the position of the plume, but also on its shape. And I didn't do further, like, more of this simulations because the parameter space is quite strong. And then in 2000, so this I did in 2016. And in 2018 or 2019, our people took the same method. And they, like Arnold and colleagues, they also took E26 flybys, and they did a lot of simulations. And then they said, like, okay, we have one fit which fits the data, and we found a plume there. Also, Gia and colleagues, they used another flyby, the E12 flyby, and they also got a good fit for having a plume in the atmosphere and get a good fit to the magnetic field data. This is nice, and we presented it as an evidence for plume activity, but it's quite ambiguous. So because, we can find some nice parameters which fit here, but there's a large parameter space. So we have to be careful with this kind of interpretation. It would be good if we would have an independent data set to prove, okay, we see it in the magnetic field, but we see it also in our data. So, but however, it's still a very good method to get some hints for plume signals. Now I would like to go to ÖAW. And so for ÖAW, we are interested in the asymmetries of the atmosphere and also the plumes. And do we really need a global magma ocean? And so in looking on Jupiter, so we have a tilt between the rotation axis and the spin axis. And due to the tilt of the rotation axis and the spin axis, we have a time-varying magnetic field at the moon. So the inducing background magnetic field varies with time, and this creates currents in a global magma ocean, for example. And this currents induce a dipole field, looks like this, if there's a global magma ocean. And this would also change a bit the magnetic field around the moon, close to the moon. So if we would fly here with the spacecraft, we would see an influence from, observe an influence from a global magma ocean on the magnetic field. And here I show you some results which were done in 2011 by Gran and colleagues, where we claimed they have some evidence for a global magma ocean at EU. And what we did is we did also MHD simulations. What we see here is the BX, BY, and BZ component. One flyby, the I-24 flyby from Galileo, and the black lines show the perturbations that were measured in the magnetic field. And when we did simulations with just the atmosphere, and we got like this green curve here, and when we added a magma ocean, like a very quite thick one, and here you see it's an ocean layer of 50 kilometers, and the connectivity was also quite high. And then this result, which is like the red line, and this seems like a nice fit, right? And and when we claimed, okay, we found an evidence for a global magma ocean, and I was interested, like, is it what do I get in my model for this? And when I investigate different asymmetries in the atmosphere, and do I still need the global magma ocean to describe the magnetic field perturbations that we see in Galileo? So I varied my atmosphere models for EU, and I have several of them. Here I just show you one. Or two. So here we have like an atmosphere with an upstream asymmetry. So here the people number density, and we have the upstream side, which is denser, when the downstream side, it is also very thin here at the poles, as you can see. The column density you see here, and then there's also, for example, the downstream asymmetry, like where we have a denser side on this side and a thinner side on the upstream side. So this is how I kind of had several models of this, also with anti-Jovanian, sub-Jovanian, day-night, and so on. I also looked on what does the Twashta volcano do, since we saw like this huge eruption with a 300 kilometers plume on Twashta. I also added Twashta in my model, and you see here Twashta is close to the North Pole, where the atmosphere is quite thin. So we have kind of a contrast, big contrast between the atmosphere and the plume. But if you look on the column densities, there's not much contrast between the atmosphere and the Twashta column density compared to Europa, where we had a factor of 100. So then I did again the simulations, and here you see the results for the simulation with just one atmosphere, and these are the results. The Twashta volcano, we have again the propagation of Alfvén waves and Alfvén wings here. And here you see where the Twashta volcano is, we have more perturbations because it's denser. So we have a small Alfvén winglet here, and when we cut through the wings, so this is the cut through the wing, the plasma comes from the left, and you see here the Twashta volcano, like this is the perturbation just due to the Twashta volcano. The plasma there is velocity is more decreased when in the outer region, but yeah, the effect is quite small compared to Europa. When I was also looking on the flybys, again, the Galileo I-24 flyby, and this is here the trajectory of the flyby. It was on the upstream side, on the day side, the closest approach. And these were the measurements. The black line is the observed magnetic field. We have strong perturbations close to the moon due to the electron impact ionization or collision heights and neutrons. And I also plotted here again the corona results. So with atmosphere and with magma ocean. So when I put my model here too, so here, what I did here, this is one model. This is my model atmosphere. It's consistent with the Hubble Space Telescope observations that we have for the neutral column density. And I get this result. So it is shown in the blue line. And you see already that here we kind of capture already the main signal or the main perturbations of the magnetic field without the global magma ocean. So why is my signal so different to corona's? And when we look on corona's atmosphere that I plotted here, this is the neutral number density. It's much thinner than my atmosphere, and it's not consistent with the observations that we have from HSD. So this is why we needed like something that gives more like so here what you see here in the red line is the pure induction signal that we get without any interaction. It's just induction signal from the induced dipole field from the ocean. And when we add this to this, we get like a perfect fit for this. So this is how we like modeled their results. But as you can see, I don't need this. I don't need the global magma ocean. And this was also my conclusion that also here we have again very careful. It's just interpreting the magnetic field results. We can model them, yeah, but it's quite ambiguous sometimes. And if the parameter space is large, so if you would not have known about how the atmosphere looks like, of course we can model when the global magma ocean, for example, on it, or even a stronger ocean. But if we are consistent with the Hubble Space Telescope observations, we don't need this global magma ocean. And last year in December, there was a press conference, the AGU, and we had new results from Juno. And so we had the results, gravitational measurements, and we saw that there's no global magma ocean on the EU, and it's just like it is consisting with a solid mantle with some melt inside. So this is how we described it. Yeah. So, and this are also my conclusions for this part. So the simulations are quite a powerful tool to study what the effects do, for example, to provide hints about plumes in the atmosphere or reveal asymmetries in the atmosphere or indicate the presence of subsurface oceans. But just modeling magnetic field data alone is not enough. We need an independent data set for this to uncover some properties. And okay, if you would have like a lot of flybys, this might be enough, but we don't have this. We have like 3 flybys or 4 flybys. And so we need different in situ direct measurements of atmospheric properties, for example. And then we can constrain the large parameter set that we have, for example, for the plume density, location, how the atmosphere looks like. And if we know this, we can use it again in our simulations to see what effect it does to the whole global plasma environment. So, and simulations are not only a powerful tool to study the Uranian system, but it's also a powerful tool to study exoplanet system. And this is my second part about, so just to bridge it, like Jupiter and the moons are also can be seen like a natural laboratory to study exoplanets. And because we have a lot of key parallels, like conducting to magnetized plasma or the formation of Alfvén wings. We have also atmospheric escape and ionization and tidal heating and so on. So here I just have a sketch again of the Jupiter system. And this is a simulation of the star-planet interaction, where you also see some Alfvén wing structures and so on. But for us here, we are studying the atmospheric circulation. So I'm not looking on the plasma environment now, but what does like the magnetic field do to the atmosphere of the planet? Not like what the atmosphere does to the environment, but more like what is happening in the atmosphere. And so we have this regime of Jupiter, and we just extend it and significantly, and then we have kind of the exoplanet system. But so we have a very exotic conditions for us, exotic conditions on the in this kind of systems. And I look on hot and ultra-hot Jupiters. This is these are Jupiter-sized gas planets, gas giant planets, which are very close to their host star. And what we see in this kind of regime, we have slow rotation. Slow rotation. So it's much slower than at Jupiter. So we have a rotation of about a few days, but on Jupiter we have like half a day. But it means that the Coriolis force is also weaker, and we have larger dynamical structures like jets and vortices in the atmosphere of exoplanets. Because we are so close, the exoplanets are so close to the host star, we have a tightly locked rotation. So there's always one side that is looking to the host star, which is very hot, and we have also a night side. That means that we have on this day side we have extreme irradiation, and this also means that we have strong atmospheric winds going from the day to the night side. And because we have this kind of very hot temperatures that you can see here, so up to 4,500 Kelvin, that means that the atmosphere is partially ionized. So we have a significant thermal ionization, and when we have this kind of ionization on the day side, then we have also coupling to the magnetic field if there's like a planetary magnetic internal field. And this is also what I'm looking on, like how does the internal magnetic field in this hot Jupiters, ultra-hot Jupiters affect the atmospheric circulation? And so far, we don't have a direct observation of the magnetic fields in the exoplanets. It's just like an indirect observation. But there are a few studies like showing that the magnetic field, if there's like an internal magnetic field, that it is stronger than like Jupiter, for example. So here we see the distance from the star, and here is the equatorial magnetic field, and this is where we have the hot Jupiters. And yeah, here you see Jupiter. So this is a study with like different observations, and yeah, we assume that that magnetic field is stronger than 10 Gauss for hot Jupiters. So, and to model this, like to study what does the magnetic field do, or what is happening in the atmosphere, to the atmospheric circulation and so on, we need a good method, and this is done by global climate models, and they simulate the 3D atmospheric dynamics. And here we work with the code XRAD, developed a lot by Ludmila and our students. So let's have a look on the code. So here are the what is solved in the code. It's like these are the hydrostatic primitive equations for the atmosphere, and this is in pressure coordinates. So the pressure is the vertical coordinate. We see the horizontal momentum where we have the geopotential and the Coriolis force, and then we have vertical momentum, continuity, and energy. And when we have some sort of radiative transfer, where we have the atmosphere like it's cooling and heating. And but you see also that we don't have a magnetic field here. So how do we get in the magnetic field in our model, since we don't use MHD models where we can self-consistently calculate the magnetic field, but we do some tricks here. So we can add in the model some additional Gaussian swing terms. This is what we do. And for this, we need some good assumptions to do this. So we start with the induction equation, which you can see here. And what we want to put we want to put a term in our momentum, which, because we know that the winds are influenced by the magnetic field. So, and when we do a lot of different assumptions, which are valid for the exoplanet system, and one also critical assumption is that the Reynolds number is smaller than 1. And when from this, where we say like the diffusive term, which is here, which dissipates the field, is the dominant one compared to the inertial one. So we can derive an assumption or like an approximation for the Lorentz force, the J cross B force, in the east-west direction. And so this is this is not new. This was already done by several people. And then from this, we can derive a term like here that we put in our momentum equation, and where the magnetic field coupling is somehow included. So moment. So if you see here, so we put it in the horizontal momentum and in an energy transfer, and this is how we include the magnetic field in our model. But I will talk about it soon. The critical assumption here is that the Reynolds number is smaller than 1. And just so I implemented it in the code, and just to give you an idea what is happening. So here we see a horizontal slice of the atmosphere at a specific pressure level. And this is the substellar point. This is the day side where you really have very high temperatures, and then you have the night side. So we have a strong temperature difference between day and night side. And when you see also this jet, we call it the eastward jet, which is going like from the east to the west in the atmosphere. And this is a model without the magnetic field drag. If I put the magnetic field in the model, I get this result. So still, like the magnetic field, the flow pattern is very similar still on the night side. And this is because on the night side, the temperatures are lower and the ionization is also lower, the thermal ionization. So on the day side, the ionization is very high. So the atmosphere is partially ionized, and we have this cut-off of the eastward jet, and we just have like a flow which is forced above the poles here. So this is you see that the magnetic field shapes the flow pattern, and also weakens the winds in the atmosphere. And now I'd like to show you some limitations of the model also. So as I said, like these assumptions are valid for Reynolds number smaller than 1. What happens if Reynolds number is larger than 1? And if I'm looking on a specific like exoplanet, which is very hot that I showed you, if I just plot the Reynolds number, so what you see here is the Reynolds number plotted for the points of the simulation. So this is the temperature and the pressure that we have got from the simulation. And then with the temperature and pressure, you can calculate the Reynolds number. And this is what we get. But what we see here, this is the day side. And in the day side, the Reynolds number is larger than 1. This is problematic for our model because when the assumptions don't work, right? And if the Reynolds number is larger than 1, that means that the inertial terms in the induction equation become dominant, not the diffusive terms anymore. So we are in this ideal magnetohydrodynamic regime. So the field lines are coupled to the plasma flow. It means also that the self-excited atmospheric dynamo might be possible. And this is driven by the by the gradients of the spatial gradients of the diffusivity. So this is what we are now like analyzing a bit or trying to understand, also with some analytical models. How can we improve the model, and how can we interpret results here? Because if you have on the day side which is very ionized, and where the Reynolds number is larger than 1, so the magnetic field is coupled to the plasma flow. When it's swept to the night side where the fields are dissipated. So that means that if these two sides are like, if the day side magnetic fields encounters the weak fields from the night side, some complex magnetic field topology is happening, and we try to kind of find like an explanation, what we see there and how can we improve the model. Yeah, this is where I stand for this project, and thank you for your attention.
Thank you very much, Aljona. I believe this is really the first talk where we really bridge the gap from the solar system plasma physicists to the exoplanets. Cool. I hope that there are questions. Who wants to have it? Okay, first, then I have to go. Okay.
I want to go back to the IO Europa issue.
Mm-hmm.
So, I mean, from your studies or your talk, I realized that you have a huge experience on these materials which produce the plasma torus, right, from IO.
Yeah.
So is there, I think the main species there of these plasma torus, I have in mind is something oxygen maybe, or what are these, sulfur? Is there also sodium also?
Yeah, I think there was sodium also.
Because only in the near future, related with the JUICE mission, I'm trying to figure out because this sodium from IO, it contaminates also the surface of Europa, I expect. Or Galilean maybe too.
Yes.
And this is, I don't know exactly, I mean, how much studies are there on that. But the idea what I would have is, you know, that these subsurface oceans, they have to conduct, they're conductive. And there is one idea that they are salty.
Yes.
And this is related with the conductivity and then this induced magnetic field. So the idea would be to figure out on the surface a kind of balance. What is delivered or contaminated externally from where IO would be a main source, I think. And then, so to get an idea what comes from external and what comes from the internal side. So that one has an idea probably on the conductivity, on the salts.
Okay, yeah.
So I don't know, maybe
I think this work was done.
Think on that a little bit,
Yes.
and maybe discuss the issues later, but it's only to somehow briefly introduce you what we plan there. Because a lot of this is on the surface. There are also observations of salts, and also this external sodium could react on the surface and produce salts which maybe then not from the ocean. So has to figure out the kind of balance.
I think it will be
in the future.
Quite hard to do it with.
So something. I mean, I contact you there as an expert in the house, I think, but it's only some.
Thank you.
Why don't you include ambipolar diffusion term in your induction equation? Despite you are dealing with the partially ionized neutral components interact differently with magnetic fields. That is quite common fact. And your induction equation is on base of just G over sigma, but it's not enough.
You mean the one for exoplanets, right?
Yeah, for any.
Yeah.
If you want to include neutrals, it's not enough just to change the diffusion term. Because there is in the generalized Ohm's law, there is a term which will produce you additional ambipolar diffusion component in the induction equation. And this, by the way, might solve you the problem of the small or big Reynolds number when you change from the day to the night side, because there will be another term.
Yeah, so far, like in our studies, the ambipolar diffusion term was kind of.
You see, electrons are frozen in to the magnetic field. Ions are mainly dragged by the neutral flux, and there is a charge separation electric field formed in the background magnetic field. And this effect is described by the generalized Ohm's law with the ambipolar diffusion term. And the control parameter for that effect is the ratio of the gyro frequency to the collisional frequency of electrons and ions. For electrons, it's much higher than unity. For the ions, the ratio is about the unity. But in the conductivity term, the value of this Cowling conductivity is a well-known Cowling conductivity involved in this game. It's controlled by the product of these ratios. And if the product is still much higher than unity, then you have an additional transverse dissipation term. And also in the magnetic induction equation and in the energy equation.
So
it's not say the critics, but to look at this effect, maybe it will resolve some.
I will have a better look. I did in the beginning, and also in our studies, it's kind of not looked into it because they say it's quite small. We did like a scale analysis. And we said, okay, but maybe in different regimes, like for the day and night side and so on, maybe we should look more like, differentiated on this ambipolar diffusion term. But in our studies, not used at all.
This is,
I mean, we know that there are subjects in it, but thanks for the comment, and I think we can continue this. I mean, we definitely come back to this at some point.
So thank you for the very interesting talk. So you must be very interested in the two-state then in the end.
Yes.
But it's not the question. So the question is about the Europa flyby. So in the magnetic field data, there was a very clear spike. I did not speak about it, but what do you know what?
I know
it's the reason for this spiky event.
Yeah, right. I looked a lot into the spike, and so far no one could really say what it is. Some people say, it's maybe like a bug or something in the measurements, but this spike is about, try to remember, I think it's a few measurement points, and it's like a few kilometers, like more than 20 kilometers for sure. Yeah, I looked into it also in our data and so on, but no, we could not find any good reason for the spike. So
it's also not described in literature, is it?
No.
Is it not described in literature?
No, like
it's said, but there's nothing here. No.
But it's like,
if we would have had good plasma data on Galileo, maybe we could have found something out. But no, we don't know what it is.
Yeah, the plasma data is also not so conclusive. Also, I mean, this, the plasma data would be nice because, like, for this plume here, which was modeled by Gia and colleagues, we did also like this magnetic field fit and so on. We got a good fit, but because it was so close for the E12 flyby, you would see something in the plasma density, but there was nothing. So if there is a plume, there would be a spike also in the plasma density, but there is nothing. So what we did, we pre-analyzed the plasma data. And suddenly we found a spike. And when we said, okay, this is evidence for plume, so maybe you have to reanalyze data to get the plasma data is not so conclusive for E26. And for the spike, I was looking a lot on this during my PhD, but I didn't find any good explanation.
Okay, I have a question about this discussion about this. You had problem with this Reynolds number and so on and so forth. You have problem because you think this is now a medium which has to be this very horizontal dominant, or what?
No.
You don't, because originally I couldn't understand your motivation. Maybe that's why I didn't understand what's the problem. I mean, if you have a large Reynolds number regime, this is the way, right? This is happening. The magnetic field is fine, but maybe your motivation was more you wanted to keep it low. That's I don't know why, but as this generalized Ohm's law in those times, but depends again on the very time scale. And I thought in general you wanted to have not small time scale, but average behavior, isn't it? That's your motivation.
Yeah, but my motivation is, so we have EXORAT, the code which is simulating the atmospheric circulation. And because magnetic field, like we expect the exoplanet to have a magnetic field. The magnetic field would change the atmospheric circulation.
Yeah, you to treat this as something drug, right?
I treat it as a drug, right? Yeah. But this I can only do if the Reynolds number is smaller than 1. If it's larger than 1, then I can't do this anymore.
Yeah, okay.
And this is like for this planet, this is the case on the day side, because the higher the temperature is, the stronger is also the ionization, the thermal ionization, and also the Reynolds number is higher, and the stronger the coupling between the magnetic field and the flows. And this is not what the model can do when we just implement a drag.
You treat it as a drug.
Yeah. Mm-hmm. If you do exoplanets which are cooler, it might be enough with the drag. But here, although when we see also our studies, we have also the drag inside, and we do it also for the very hot Jupiters. And we don't discuss the Reynolds number too much. But yeah, this is something critical here.
Thank you.
I don't know. Yeah, exactly. The famous finding work. I just want to put a little bit in perspective. So far, people in exoplanet science have basically just put a constant, and Aljona has unraveled all of this so that we get a better understanding what actually is going on in the atmospheres. And so now this is actually the first time. I mean, we knew that they're changing ionization regimes, right? They're partly ionized, etc. But it's the first time we begin actually to see what we can do and where we expect a partially coupled atmosphere. And I think this is already quite exciting to see that the day side potentially produces its own induced magnetic field on top of everything else.
So, and with this, I would like that we all thank Aljona again for a very nice talk. We have actually 2 seminars. So on Tuesday, we have a seminar on the 10th anniversary of the MAVEN mission at Mars, given by Dr. Christian Marcel from the Institut de Recherche und Astrophysique et Planetologie de Toulouse. And on Thursday, we have our colloquium from swarm to nanomaxat. That is given by Dr. Jean-Michel Léger from CEPALETI. So I hope that you enjoyed and talked. Unfortunately, will not be here, but I hope that you all will come, all that are here, will come there and get yourself inspired by these people that are willing to come here. Thank you very much.
Ja,